Welcome back to math class. This is Wit. This video is intended to help you understand the notes and on our solving one-step equations. So let's get started. First, let's do a little bit of a warm-up and engage our brains. I want you to take a couple minutes, press pause on the video if you need to, just to see which of these figures share the same value. So go ahead and hit pause for a minute or two and consider. Okay, hopefully you chose this one, and this one. This first one has 3 red and 6 blue dots. This one also has 3 red and 6 blue dots. Again, 3 red, 6 blue. But if you notice, they all look a little different. This one's got a group of the 3 reds together, separated. There's the 6 blue. Here we've got 1 red with 2 blues, repeated 3 times. And here they're all together in one big group. Now the other ones are not, because this one only has 2 red and 4 blue, and this one is also separated by lines, but there's not enough blue ones for it to match. So we can see that things can have the same value even if they're arranged differently, and hopefully that reminds you of when we studied the properties of rational numbers, how we know we can use things like the associative property or distributive property to rearrange and look at equations in new ways or expressions in new ways. So that just kind of gets our brain thinking about how things can move around and still keep the same value. Let's recall some important words, and I know that I begin every lesson with this, but it's really important that we all understand what it is we're talking about and that we know what that's called. So a variable, we know that that is a symbol that represents an unknown value. So remember, it varies. X, Y, Z, M, N, we generally represent them with letters, but it doesn't have to be a letter, it can be anything. But we know that that value might change depending on what the problem is. And the coefficient, remember that's the co-pilot for that variable. Goodness, I'm making a mess on the screen here. That's the co-pilot for that variable, meaning it is the number that's in front of the variable. It's in front of the variable, and it's important because it has a very specific job. That number in front of the variable is a multiplier, right? It tells us how many of that thing we have. So if we have an x, but we look at it, multiplier, if we look at it, say we have x, that's our variable, 2 is our copilot, well, that really tells us whatever value we find of x, there's 2 of them. We're going to multiply it by 2. So we've got the coefficient is the 2 and the variable is the x. So I've moved that example of 2x to the top of the screen just so you can see it. And again, the 2 is the coefficient and the x is the variable. Now we've been dealing a lot with expressions. Now an expression is just a group of terms that they represent a value. So they hold a specific value. Let's, for what we're doing today, that's what we're represent a value. And it can have, inside of it, it can have multiplication, it can have addition, it can have subtraction. You can use any of those operators that we've been dealing with, any of those operations. So 2x, although it's a variable and a coefficient, it is also an expression. So this is an expression because it represents a specific value. Okay? Now the difference between an expression and an equation is generally a number sentence that sets 2 values or expressions equal to each other. So that is equal to each other. That's what's important there, is that in an expression, you don't see an equal sign, but in an equation, you definitely do. And if you see that beginning of the word equa, that looks a lot like equation, right? So let's see, if I took that example of 2, which is my coefficient, and x, which is being multiplied by 2, and now let's say I set it equal to 6. Let's say 6. Well, now this whole thing went from being an expression to an equation, okay? So this is now an equation. When it's just the one side without the equal sign, it's an expression. And I didn't put it on here, but we all know that 6 is a number by itself. We call that a constant because 6 is constantly going to be 6. It's not going to change, okay? And now what is a solution? With what we're dealing with, we want to know that a solution is something very specific. A lot of times we've just thought of it as an answer, but I want you to be clear on what a solution is in our math class. A solution is a value for the variable. It's a value for the variable that makes the expression true, or that makes the equation true, okay? Let's say it makes the statement true. Now, because our example doesn't have very difficult math, we can probably just look at that and know that 2 times what gives us 6? Well, that has to be 3, obviously. So if we said x equals 3, that would be our solution, because we know that 2 times 3 equals 6. Well, 2 times 3 is 6, and 6 does equal 6. That is true. Therefore, our solution, that x equals 3, is correct. Now we're going to engage our brains a little bit and go back to some things that we know. Let's think about this. The expression or the term 1, just the number 1, that's a constant. We know about that. And we know that the opposite of 1 is negative 1. And how can we prove that? Well, 1 plus a negative 1 equals 0. So we know that we're looking for something that is the opposite, and we know that the opposite, or we call it the additive inverse, right, will add to the number, and it'll make it 0. It'll make the value 0. It'll balance it out right at 0 on a number line. So I want you to take a minute and let's think about these other ones. So 3, what is the opposite of 3? If you look on the number line, 3 is 3 spaces away from 0 to the right. Well, if we go the opposite way, an equal amount, we'll get negative 3. And how can we prove that we know we're right? Well, 3 plus the opposite, negative 3, equals 0, or that's the additive inverse. But what if I start with a negative number, like negative 7? And the opposite would go in the other direction from 0, and we know that negative 7 plus 7 equals 0. Does that work with all rational numbers? What if we have not only a negative, but a fraction? What would the opposite be of negative 1/2? That's right, it'd be positive 1/2. So negative 1/2, we can prove it by saying plus a positive 1/2 will get us back to 0 on the number line. Now that we're dealing with more algebra and we're introducing these variables, what would that look like if I had a positive x? So not a number that I can find on the number line, but just the letter x, something that varies. What would the opposite of positive x be? Well, we're going to follow the same logic, a negative x. And we can prove that or test it by saying that x, what we had, plus a negative x equals 0. And that's true. Remember that anytime we write addition, when you add a negative, that's the same thing as subtracting. You could have looked at it as x minus x equals 0, because we know that those two situations are interchangeable. A minus and adding a negative, same thing. We talked about that in the beginning of the year. So knowing that, so we've just explored that, we've engaged it, it's information we already knew, but we learned how to write it down in a proof. Let's recall what we know about an additive inverse. Well, we know that the additive inverse adds to make 0. And we have a whole bunch of examples of that. We have a whole bunch of examples of that. That's what we just did. It adds with the number to make it 0. We might also think of it as the opposite. And what happens when we add or subtract 0 to a value? So 0 is important. We know that the identity property tells us that you can add 0 to any number and it keeps its value. It stays the same. It keeps its identity. Okay? So, for example, 7 plus 0 equals 7, or even 7 minus 0 equals 7. So 0 might come in handy if we need to keep something's identity, okay? So if we want something to be 0, it doesn't matter if we add or subtract 0. We wouldn't even have to write that down, right? We could have written this down as 7 just equals 0, 7 equals 0. So that might be a piece of information that we store away and save for later. Now let's engage our brain this time thinking about if we used multiplication. So this time let's think about, we did the additive inverse, now let's think about the multiplicative inverse. And we've talked about that off and on all year, and it is written over on the board. Multiplicative inverse. Well, right here this first example tells us if the expression is just 2, if the term is 2, and we think of the multiplicative inverse, or the opposite when we're multiplying. Oh, that's not a very good example, is it? Because it looks like an X. So let me actually write out the word multiply. When we multiply 2 and 1/2, right? So 2 times 1/2 equals 1. Okay, so half of 2 is 1. All right, so the multiplicative inverse, it multiplies to 1. Okay, so let's try that with 5. Well, we only want 1. We want it to equal 1. So we're going to say, well, 5, which is the same thing as 5 over 1. Well, 1/5 of 5. Does that make sense? 5 times 1/5. What is 1/5 of 5? It's just 1. Does it matter if it's negative? Well, if it's negative and we want it to equal 1, we know that if we take a positive times a positive, we will get a positive. But we also know that a negative times a negative will give us a positive. And we're trying to get a positive 1, right? So we need to make sure that we keep that negative sign with this. So I'm going to say, instead of just taking half of 2, I'm going to have to take negative half of 2. And let's see if that works. So negative 2 times a negative 1/2. Well, half of 2 is still 1, and a negative times a negative makes it a positive, so that indeed does work. And this last one, negative 3/5. Let's look at that. So negative 3/5. Well, I'm going to need something that gives me 1. So I know it's going to have to be negative. Well, what happens when I flip this upside down? The multiplicative inverse, we know, is just that flip. So I'm going to do negative 5/3. And that does indeed give me 1, because straight across the top, I've got a negative 3 times a negative 5, which is 15. And on the bottom, I've got a positive 5 times a positive 3, which gives me 15. And 15 divided by 15 is just 1. So this is going to be working the same way with x, or with any variable that we put in there. If x over 1 is our expression, then the opposite of it would be 1 over x. And we know that's true because x over 1 times 1 over x. Well, that gives us just across the top, x times 1 is just x. And across the bottom, 1 times x is x. And x over x, well, that's just 1. The same thing as 2 over 2 is just 1, or 7 over 7 is just 1, or 15 over 15 is just 1. So what did that help us recall? The multiplicative inverse. Sometimes we call it the reciprocal. You might have heard it called the flip. Well, what we do is it multiplies with the original number, multiplies to make 1. And why is 1 important? Why is a positive 1 important? Well, when we multiply any value or divide any value by 1, it keeps its identity, right? And that kind of goes back, identity. That goes back to that identity property like we talked about with addition. Okay, sorry about that. I paused the video for just a second because I saw a spider and freaked out a little bit, but I'm okay now, and I'm not sure if I remember what I'm talking about, but I believe I was talking about multiplicative inverse and how getting a 1 when we're multiplying or dividing would be helpful, because we know that anything divided by or multiplied by 1 keeps its value. And that's important because we've talked about keeping value. Like even in that first warm-up when we said, well, how is this thing like the other thing, only it looks different? Well, because it has the same value. So let's go ahead and move on. So let's consider, and before we work on this slide, I do want you to notice that I made a mistake on your guys' copy, I believe, and I fixed it on mine, but you just might want to scratch through, and that last one should say additive inverse. So what do we know about two numbers that are multiplicative inverses or reciprocals? Well, if we look back at these, what do we know about two? Well, they multiply to give us a value of 1. They multiply to 1. And what can we say about the signs of reciprocals? Well, when we had, when we did negative 2 over 1 times negative 1 over 2, that worked, right? That gave us a positive. And because we know that a positive times a positive gives us a positive, and a negative times a negative gives us a positive, we know that the reciprocals have to have the same sign. They're going to have the same sign as the original term, okay? But now, what do we know about the signs of additive inverse? So that additive inverse was like 1 plus negative 1, and we want them to add up to 0. Well, they had opposite signs. So we know that the signs of an additive inverse, they're going to be opposite signs. So if one is positive, the other must be negative. But, because we want them to end up at 0, but with the multiplicative inverse or reciprocals, we know that they have to have the same sign, because that's the only way it's going to get us to a positive 1. Now, we're going to use all that information today to work on our key idea of how do we solve equations. How do we solve equations? Well, that first example that I gave you is pretty simple. We knew that 2 times 3 gave us 6. That's easy. But there's an actual specific method and a procedure that helps us do it efficiently without making mistakes. So the goal of solving equations is to get one copy of the variable. So the goal is to get one single copy of the variable alone on one side of the equal sign. And how are we going to do that? Well, we are going to be using inverse operations. So when we get a solution, when we solve, we're looking for a value of that variable that makes the statement true. So we want to get it down to where there's just one single copy on one side. So for example, when we had that 2x equals 6, and I said the solution was x equals 3, notice that there's only one copy of x, and it's on the opposite side of the equal sign from the number. So that's what we're going for. So let's go back and remember, what do we know? Well, we know already that GEMS is for simplifying. So we use that order of operations when we do math, right? When we do math, we go through and we start with grouping symbols, and then we do exponents, and then we multiply and divide left to right and subtract and add left to right until we get down to the simplest answer. That is for simplifying. That's how we simplify. Obviously spelling, not my strong suit. You guys are seeing it more than normal today. That is how we simplify. Simplify. But when we're doing, when we're solving is different. Solving, like I said, is going to use inverse operations. So we've talked about opposites, inverse. That's how we're going to undo any math that we've had so far. How do we undo the math? Well, we're going to use SMEG. We're going to do everything in reverse. Okay, so if GEMS is for simplifying, SMEG is for solving. Okay, so we're going to SMEG to undo everything. So that means we're first going to look at what can be subtracted or added, then multiplied or divided. Then we're going to look at exponents, and then we'll look at any grouping symbols. And what does that look like? Well, remember that since the directions tell us to solve for x, we know we're going to do everything in reverse order. We're going to SMEG because it's the inverse of GEMS, okay? So let's look at this. So right now we see x plus 10 equals 20. So since we're going to use SMEG, we're going to try and undo anything we see close to the x to try and get x alone on one side. And right now, the only other thing on that side of the equal sign with the x is this plus 10. Well, we need to get rid of that. So let's start with subtraction and addition. Is there any subtraction or addition next to the x? And there is. There's that plus 10. And we want to get nothing over there with it. So we want there to be 0 over on the side of the x. So how could we turn 10 into 0? Well, we can use the opposite. We can use the additive inverse because we're adding and subtracting. We're going to use the additive inverse. So the opposite of plus 10 is minus 10. Now, whatever we do to one side of an equation, we must do to the other side. That's the only way to keep it balanced, to keep it the same. So what I do to one side, I do to the other side. So I'm going to keep that equal sign exactly where it is. And then I'm going to just do what it says to do here. Well, I've got x plus 10 minus 10. Well, plus 10 and minus 10, they turn into 0, right? They turn into 0. And x plus 0 is just the same thing as x. So we've got x over there. Now let's look at the other side. 20 minus 10. 20 minus 10 is just 10. Okay, so did we achieve our goal? Our goal is to get a single copy of x alone on one side. And on the left side, I see that x is alone. There's just a single copy of it. And it is set equal to 10. So we believe that x is our solution. How can we test that to see? Well, we think that x is our solution. So we can always, or that 10 is our solution. So we can take the 10 and substitute it in where the x is and see if that's true. So we've got the 10 that we think it is, right? And then we'll just copy down the rest of it. Plus 10 equals 20. So now to check it, we just need to simplify. So we're going back to GEMS now because now we're just simplifying. Well, on the left side, 10 plus 10 is 20. We didn't do anything to the right side. Does 20 equal 20? Is that true? Yes. So we know that 10 is indeed the solution. That's how it works for addition. Let's try with subtraction. Well, looking at the next one, x minus 10 equals 20. Well, what is the opposite or the inverse of minus 10? Plus 10. Whatever we do to one side, we have to do to the other. So I'm going to carry down that equal sign. That has to stay there. And then I'm just going to perform that operation. So if I have a minus 10 and a plus 10, they equal 0. So x plus 0 is the same thing as just x. And 20 plus 10 That's 30. And we will know if that's the right answer if we just plug 30 in there. We substitute it in there to see if that's the same thing. So 30, and then I'll continue on with the original, minus 10 equals 20. So 30 minus 10 is 20. Is that equal to 20? Yep. So I know that x equals 30 is the correct solution. Now this also works with multiplication and division. So right now I see that 10 times x equals 20, right? 10 is that coefficient. It's a multiplier. What is the opposite or the inverse of times 10? Well, we can divide both sides by 10. Divide both sides by 10. So I'm going to keep that equal sign right there because that's important. Didn't go anywhere. And 10 divided by 10, well, that's just 1. And we know that 1x is the same thing as x when we're multiplying, because we talked about how if we multiply anything by 1, it just stays the same. So let's go ahead and just write x on the left side. And 20 divided by 10, well, 10 goes into 20 2 times. So I believe that my solution is 2. How do I know for sure? I can always take that 2, substitute it in where the x is to see if it gives me a correct result. So 10 times 2, 10 times 2, does that equal 20? Well, 10 times 2 is 20. I still have 20 on the other side. 20 does equal 20. That is a true statement. Therefore, x equals 2 is a solution. Now, this one's a little bit different, but you still follow the same rules with division, okay? So we're going to think, what is the opposite of divide by 10? We can kind of think of this in two ways. The opposite of divide by 10 is to take something times 10. What I do to one side, I have to do to the other. I'm going to keep that equal sign. Well, if I have x divided by 10 times 10, or 10 over 1, well, on the top, I'm going to get 10x, and on the bottom, I'm going to get 10, and we knew that those just cancel out. So I have x. But you can just remember that times 10 and divided by 10, you do it, then you undo it, it gets rid of it. And then 20 times 10 is 200. How can we know for sure that we got the correct solution? I'm going to plug it in where the x is. So I'm going to say that 200, because that's what I think my x is, divided by 10 equals 20. Well, let's think about that. 200, 10 goes in there 20 times. 20 does indeed equal 20. I know that this is a correct solution. So remember, we're working in opposite. We're working in inverse. So the first thing you'll look for, is there anything subtracted or added to x, or is there anything multiplied or divided by x? And because we're working with one-step equations, we're not going to get as far as doing anything like exponents or grouping today. But just remember, you want to perform that inverse operation. So what's left to do with today's lesson? You have 4 practice problems. And I want you to specifically use the inverse operations to solve for x. Now you can always check it by substituting it back in. Some of these you're able to just know, right? A lot of these will get an intuitive sense of what the answer should be, but it's important to me that you use your inverse operations. So if you see addition, I want you to do subtraction. If you see subtraction, I want you to do addition. And be very careful that you use all the rules that we know about signs. So when multiplying and dividing, we know that 2 positives or 2 negatives will give us a positive. If they're different, then you'll get a negative. And remember, you can always use a number line or integer chips when adding and subtracting positives and negatives. Or you can sing the song. Remember, it's on the yellow poster at the back of the room. Same signs add and keep, different signs subtract. Remember that one? Keep the sign of the larger number, then you'll be exact. And that will help you find the correct answer for any that are positives and negatives using addition and subtraction. So go ahead, and before you do anything else, you are to finish this practice page, so the 4 problems. Once you get that done, you may go ahead and attempt some work on the choice board.